Okay, so in the next example, we want to also determine the range of a function whose domain we have already seen. But this time around, we're going to consider a function like this one. So this is going to be our next example. And in this case, we have f of x comma y. And this time we have this being equals to 25 minus x squared minus y squared. So we saw how you get the range when a square root is involved. And for starters, you know to say a square root can never give you a negative solution. So we expect that the range is going to have only positive solutions. But in an event that under the square root, you have a number popping out or present under that square root, what changes? In the previous example, we saw to say that if you had a term like this one, and then you only have the two variables present there, we saw that our range was only from 0 included, and this was going all the way up to positive infinity. But what if a number is present? What changes? Well, the number change kind of changes the layout of the question. And the best way to actually view this is if you tried to sketch it. Now, the concept here is quite simple. If you did try to sketch this expression, here's what you would see. Firstly, this part here, f of x comma y, because it's an output you get depending on what x is and what y is, you can view this as a new variable z, which is a result of x and y. So you can look at this as if it's the third variable z, such that it's equals to 25 minus x squared minus y squared. So this is how our expression comes out. Now, if you tried to square this, square both sides, you basically end up with a part where you have z squared equal to 25 minus x squared minus y squared. And when you look at this term, it simplifies to give you x squared plus y squared plus z squared is equals to 25. What expression is this? What do you think this gives you if you look at it closely? What does this give you? What shape is that? Can you? Yes, that is a sphere. So this is giving you a sphere. Now, picturing the sphere, you don't have to do what I've just done every time when you have an expression like this, but I just wanted you to get to have an image of what we are kind of describing here. We're working with a sphere, but not necessarily a full sphere. What do I mean? Well, if we just track back a little bit and just look at it from this part, the concept of a sphere, especially if a sphere is described by this, it has two properties that you need to keep in mind. One, this sphere has radius r is equals to pi. That's one thing. Then the second thing, the sphere is centered at the origin, 0, 0, 0. So that is the sphere whose equation is going to be given by that. But when you look at the expression we had, where you only had z being equal to, and then the other side we had 25 minus x squared minus y squared. I think this is what we had, is it? Yes, that is what we had there. Now, it's like I've gotten the same expression for the sphere that we're describing earlier on. But now I am saying that in this case, you are only looking at positive values. It is still that sphere, but the values of z are restricted to only positive terms. Because you know when you square root, perhaps we should have added plus or minus. But the fact that we only have the positive term here, it implies that in our sphere, we are only looking for the section where we only have positive values of z. What does that then translate into? Well, if you try to sketch this expression, if I was to place z somewhere here, and then we have, let's say, x somewhere on this side, and we have, let's say, y somewhere this side, what would we have? How would it look like? Well, in this case, here's what we get. Firstly, when the smallest value of z we can ever have because of the square root, would be when z is equals to 0. The square root ensures that all the values of z will be positive, as I pointed out. But the smallest possible solution is going to be when z being equals to 0. So z being equals to 0 becomes the smallest possible solution, and you will get z equals to 0 for what terms? So what we'd expect is that it's basically going to be a maximum somewhere this side, at the base somewhere that side, so that this is the radius of that sphere. And this is also the radius of that sphere. But what happens in this case? Well, for this circle that we have drawn there, what you have to get is that 1, the radius is maximum, and 2, z is equals to 0. When do we expect z to be equals to 0? When the argument of the square root there is equals to 0. So in other words, inside there, we're looking at 25 minus x squared minus y squared is equals to 0. So for just that circle we have drawn there, we're looking at x squared plus y squared being equals to 25. That is what we have. So this is a circle of radius 25. Now, what happens? You see, when you reduce the values of x, and as in this sum here, when you reduce it, why am I saying reduce it? Well, you can't increase it, because if you were to increase this sum, it would imply that the argument of the square root would end up being negative. Of course, you know, to say if I was to just play around with the square root, just factor out that negative. If I factored out the negative, I would have x squared plus y squared like that. So if I was to increase this sum so that maybe it gives me something greater than 25, you know that when that sum gives you something greater than 25, you have 25 minus whatever that sum is, which will give you a negative term under the square root, which you do not want. So in other words, in this case, remember our domain was such that the values of x squared plus y squared had to be less than or equal to 25. So 25 was the maximum we were allowed to get from this sum here. Everything else was supposed to be smaller. Now what happens? It's like we have 25 as a fixed term, but this sum can only give you 25 as its maximum. So from 25, when we less 25, we get 0. But when we less a number, any number less than 25, we can even try. Let's less something like 16. When you less any number less than 25, say 25 minus 16, you will get 9. And so this is going to be 9, so that the square root reduces to just root 9. And root 9 comes to give you what? It comes to give you 3. So in this case, you end up somewhere here. So when the sum x squared plus y squared ends up giving you a term like 16, we see that now it's like I'm saying that sum is translating to a circle of radius 4. A circle of radius 4, we end up with z being equal to what? Z ends up being equal to 3. So it's like now we're ending up somewhere here, but in this case, we're dealing with a circle of radius 3. So that circle would be something a little bit smaller because the radius is now a bit smaller, and it's going to have radius 3. Just move it up a little bit. Yes, something like that. Let's check one more thing. Next up, what if the sum now reduces even further from 16? What if the sum goes to 9? Notice that in this case, I am picking perfect squares so that it's easy for me to actually evaluate the square root when it comes out. So in this case, you're going to have the square root of 25 is fixed, but now I'm saying that x squared minus y squared ends up giving us 9. So it's going to be minus 9, and you know 25 minus 9 is going to be 16. So we're now dealing with root 16, and root 16 is going to give us 4. What are we saying here? When the sum x squared minus y squared reduces, in this case, I am saying when x squared minus y squared or plus y squared ends up being equal to 9, notice that now it's the circle of radius 3. So when the radius reduces for our circle, meaning it is now even smaller, let's make it even smaller. we see that in this case, the value of z increases a little bit more. So it's like for this one, let me keep it just where it is, but let me just lower it a bit. And then this one, let's drop it up just a notch. So the value of z has also increased. What you have to see is that it's just the same sphere we described earlier on, but now we are just seeing the top part of the sphere. So it's like this is the top part of the sphere. It keeps going up until when we have a circle of radius 0 there. So we have, this is the sphere that is being described there. And of course, you have to picture this in 3 dimensions. I was trying as much as possible to give it in 3 dimensions, but generally it's made up of smaller rings, and all these rings are being controlled by a circle of radius x squared plus y squared being less than or equal to 25. With the bigger one, the one at the bottom when z is equals to 0 here, occurring when x squared plus y squared is equals to 25. Okay, so a better image of what I was trying to present would be something that looks like this here. So when you look at this, it shows exactly what I was trying to describe there, where in this case, we're describing that expression. Let's just get the formula back up. So describing that expression f of x comma y. So this is f of x comma y, and this is given by root 25 minus x squared minus y squared. So look at this expression. When this sum here, or when minus x squared minus y squared they give us a minus 25, we're going to have 25 minus 25, which is 0. We notice that we will be dealing with a circle which is basically in the xy plane, which is this circle down there. So that is the circle that we'll be dealing with. Now notice that this is a circle of maximum radius, which is this one described this side. When we view the same semisphere or half sphere from the top, so that is the circle that we'll be seeing there. But when basically I'm literally just looking at the same expression, but we're saying it's like I've rewritten it and I'm saying x comma y is equals to root 25, and then we have minus x squared plus y squared. So when this sum here reduces, meaning that now the radius of the circle we're talking about is a little bit smaller, it will mean that now we're dealing with a circle, let's say, of a smaller radius, which is a smaller ring, like this. But it's not just rings that you're dealing with, it's a million of these rings put together, making that, that sphere of ours. Yeah, so that is going to look like this. Now the radius is just much, much smaller, coming only up to this. And when the radius is reduced again, we're looking at a sphere that comes only up to here, and so on. As the radius keeps reducing, notice that when you look at it from the side, the value of z keeps going up. Initially, the value of z was 0 when the radius was 5. But now when the radius is, let's say for that ring, when the radius is something like a 3, we see that the solution or the value of z also would increase. Eventually, when the radius of our circle is a 0, meaning that this term here, minus x squared minus y squared, when they end up giving us 0, then this term will get its maximum solution, which will basically just be root 25. And in this case, we will get a 5 at the top there. So basically, this is how it goes. Now, by seeing how that diagram looks like, you can now try to predict what the range for such a function would be. Now, the range will be the smallest value of z in this description, which is 0 when this term here is equals to 25. And the maximum value of z is going to be 5. So the maximum value of z is going to be 5, and 5 is going to occur on the diagram right at the top there. But mathematically speaking, 5 is going to come out when x squared plus y squared is equal to 0. So that will be dealing with only root 25. So this is going to be our range from 0 all the way up to 5. Okay, so I hope you were able to see how this plays out. Now we're going to describe one more example, but this time we'll try to just look at it. I won't try to explain with these diagrams. You can always try to sketch them, but you should be able to just have an idea of how it is going so that you can make a conclusion even without having that diagram down. Okay, so let's look at another example. And in this case, we will not have a sphere or something circular. Now look at what we're now seeing here. In example number 6, we have f of x comma y, and this time we have root 36 minus 9x squared minus 4y squared. So what are we dealing with in this case? Well, in this example, here's what you're seeing. Firstly, we did see the domain, and I hope you remember what we did for the domain. We basically just got the argument here equated and say the argument must be greater than or equal to 0. So because of that, we ended up having that conclusion that we were dealing with an ellipse. So the ellipse that we ended up having there was x squared. This was plus y squared, and this ended up being over 4, and this ended up being over 9, and this was greater than or equal to 1. How does this translate? Well, just like we saw for that sphere that we ended up with, it's only going to give us positive solution because we are seeing a square root in play there. So the square root can only give us positive solutions unless if a question does say we have a plus and a minus there. But because we do not have that, we're only going to have the top part of that ellipse, which is above the xy plane. So basically, it's going to be something similar to this, where we're only looking at the positive part or the piece of the ellipse, which is going to be above the xy plane. So how does that conclude in terms of, yeah? Have a question?
You can explain again why the solution will only be based on the but
Okay. So it's all about, it's basically a similar concept with how we concluded that that sphere will only consider the top part, the positive part of the sphere. And ideally, what we have inside here can be seen to be an ellipse, just as we saw for the sphere there. But the argument here is this. When you have an expression like this, I'm sure you remember from our earlier discussions that a square root can never give out negative solutions. You remember that? Do you remember?
yes.
Yeah. In fact, if you had something like x squared minus y squared here, and then you had the square root something like this, we sort to say for an expression like this one, I think this was what we did last time. For an expression like this one, the range for such a function can never have negative solutions, but everything else is fair game. So because of that, because we cannot have negative solutions, we went as far down as possible. The starting point ended up being 0 because any further down would be negative. So we say that the range is going to start from 0, but from there we can only go up. So we ended up going from 0 all the way up to positive infinity. Now, if we are given something like, let's say a number, in this case we're dealing with, that is 36. In this case, we have 36 minus, that is 9x squared minus, that is 4y squared. Okay, so this is what we have in this case. It's a similar technique even here. This expression, the lowest value we can have here is a 0. We can't go lower than a 0. So the only question is how far up do we have to go? Unlike this one where we can go up, as far up as possible, for this one, it's not the case. Why? Because we keep on subtracting from 36. As these keep on increasing, in fact, when I rewrite this expression, we see that it becomes root 36 minus, I've just factored out that negative, so that I have 9x squared minus 4y squared. We see that in this case, as I keep going up, and this is plus here, as this term keeps on increasing, we see that we keep on subtracting from 36. 36 will have